Hey everybody, this is your review of the Chapter 13 exercises, beginning Part 1, page 263. So here we go. Number 1, stand on the bathroom scale. You look at your weight. Whoa! This corona quarantine thing has been causing me to put on some extra weight there. When you lift one foot off, so you're standing on one foot, does the reading change? Let's try it, okay? Right here. All right, lifting one foot, lifting one foot and looking at the reading on the scale. Does it still say the same thing it said before? What do you think? Yes, it does. So the question is, does a scale read force or pressure? Well, right now on 2 feet, my weight is spread out over a larger area, so there's clearly less pressure. On 1 foot, my weight is concentrated on a smaller area, so there's more pressure. But the scale's reading didn't change, so clearly the scale does not read pressure, the scale reads force. We move on to number 2. If you're stuck in bed for a long time, maybe with a cough and fever, you are less likely to develop bed sores on your body if you are on a water bed. Why is that? Well, what's a water bed do? Basic question here is, why does a water bed put less stress on your body, or why is a water bed more comfortable? Because what does a water bed do? It kind of wraps around you and it touches more body parts because you sink into it. It's softer. What does that do for you? It spreads out your weight over a larger area as the water wraps around your body. If your weight is being spread out over a larger area, as you well know, because pressure equals force divided by area, you have less pressure, less force on each square inch of your body, and you're less likely to get bed sores from laying there for a long time. Number 3, why does a sharp knife cut better than a dull knife? Well, what's the difference? If we were to look at a cross-sectional view of a knife, looking at the blade of the knife might be like this, okay? A sharp knife has a little tiny point down here, whereas a dull knife will have a more rounded point down here. Well, the difference is this one has a very, very small surface area in contact with whatever it is you're trying to cut, such as your steak. Whereas this dull knife has a larger area of contact with the steak. So what's the difference? You applied perhaps the same force with either knife, but this one is over a very small area, so it's a very high pressure. This one is spread out over a larger area, so it's much lower pressure. It's actually the pressure that forces itself down through the steak. So it's all about pressure. A sharp knife has greater pressure under the blade than a dull knife. And we move on to number 4. Water faucets. In your house, would you expect to have a difference in pressures between upstairs and downstairs? Well, the plumbing in your house is actually a very weird shaped container. All these pipes go together to make one container, and they go someplace off far away, perhaps to a water tower where the water surface level is way up there. So your faucets are in a container of water, and your upstairs faucets are not as deep in this container as your downstairs faucets. Therefore, you are indeed going to have greater pressure in the downstairs faucets, guaranteed. Is it enough pressure a difference for you to be able to notice it? I don't know. I've never thought about it at home. How would you even know for sure that there's a difference? But yes, the lower you go in that container, the lower you go in your house, the farther down your faucet is, the more pressure you're going to have. And that brings us to number 5. Which do you suppose exerts more pressure on the ground? Well, we know this one. We talked about this extensively in class. An elephant or a lady standing on spike heels. Definitely the lady standing on spike heels has more pressure. We're going to bypass the rest of the discussion on that because we've already covered it. I trust you took note of the picture there on number 6, which I didn't assign, but he's able to walk across the broken glass because, just like with a bed of nails, the pressure on each individual piece of glass is not enough to puncture your foot because there are so many of them. It's all about pressure. Number 7. Why does your body get more rest when you're lying than when you're sitting? And why is blood pressure measured in the upper arm at the elevation of your heart? Is blood pressure in your legs greater? 3 things at once here. When you're standing up, your heart is right about here, and the heart has to pump blood all the way up a couple of feet to the top of your head. But when you're laying down, your heart doesn't have to pump blood nearly as far upward. So when you're in this position, your heart is deeper in this container of blood. Laying down, your heart is not nearly as deep in the container. So when you're standing up, the heart is under greater pressure. It has to force the blood farther up. It has to work harder. It's as simple as that. Why is blood pressure measured in the upper arm at the elevation of your heart? Well, I guess I'm not certain myself, but at the elevation of the heart, your blood pressure here is going to be equal to the pressure here. And I guess the real question is, what is the pressure at the elevation of your heart? Because up here, the pressure will be lower. Down there, the pressure will be greater. In fact, yes, is blood pressure greater in your legs? Yes. You would expect the blood pressure in your legs to be greater because your legs are deeper in this container of blood. I believe in one of the previous videos I did show you what happens when I put my hand up high when the veins go flat, or put my hand down low, and I'm not going to do it again right now, where your veins all get bugged out and really gross looking, because down there there's more pressure, up here there's less pressure. Let's look at number 8. Oh, I like number 8. 8 is kind of cool. Which teapot holds more liquid? It's kind of a trick question. Let's see, where I have another file here. One moment, let me bring this up. There it is. Okay, here we have our 2 teapots. Question is, which one holds more liquid? Well, it's kind of a trick question because neither one is, this one, the liquid cannot go any higher than right there, because any higher it's going to come out the spout. Well, guess what? This one, same thing. Any higher, it's going to come out the spout. So they both hold the same amount. All this up here is wasted space. But I want to show you something I think is kind of cool about this. Something off topic here, and that is this. When I first saw these, it looked to me like, I don't know, I think there's another trick to the question, because this one is clearly wider than that one. This one is tall and skinny, this one's short but wide. This one looks like it holds more than that one, clearly. Haha, yeah, I caught him on that one. Well, I took out a measuring device called dividers that draftsmen use, and I measured the 2 pots. And what I discovered was this. If I take this guy up and move him over here, watch this. They are identical. The only difference is the extra few inches at the top of the pot on the left. They actually are the same width, exactly. Hard to believe when you see it like this, but true. It's an optical illusion, a very simple optical illusion. This one looks wider because it's shorter, but it actually is not wider at all. It is actually precisely the same. I know it's precisely the same because I created it using electronics. I cloned the first one and then shortened it. So I know they're the same. Pretty neat, huh? Okay, number 9. The sketch shows the reservoir that supplies water to a farm. It's made of wood and reinforced with metal hoops. Why is it elevated? Well, by elevating it, you get deeper, you get more, I should say, you get more depth from the top of the water down to your hose or whatever at the bottom. The higher the water is, the deeper you are in that container of water, and therefore the greater the pressure down here at your hose. The higher you can lift the water, the more pressure you're going to have at your hose. So part B, though, says, why are the hoops closer together near the bottom of the tank? Well, that's where the wood has to be held together more tightly. I mean, those metal hoops are expensive. You know, you don't want to have to use them where you don't need them, but you need more support at the bottom, because at the bottom, that's where the pressure is the greatest, and you've got to hold that thing together more tightly at the bottom than at the top, where the pressure is low. And I do have another, I don't know if it really helps any, but I have another little thing here. So here's the concept. Pressure equals weight density times depth. The density of the water is not going to change, but the depth in the water certainly is. Oh, and by the way, regarding the test you're going to soon be taking, yes, the only real variable here is depth, but pressure also depends on the weight density. For instance, if you're talking about water, water has one particular weight density. It's about 10 newtons per liter. But mercury would be about 13 times as much, so that must be about 130 newtons per liter. So yes, I say that depth is the only real variable because we're assuming you're staying within one liquid and that the weight density is not going to change in that liquid. But you can have different liquids. So yes, your pressure does depend on both the weight density and on the depth. What it doesn't depend on is the shape of the container or how wide the body of fluid is. Whether you're talking about this much mercury or that much mercury, it still doesn't matter. All that matters is how deep you are in it. So pressure does indeed depend on both weight density and on depth. But not on the shape of the container. Moving on to, let's see, oh yes, and in this illustration again, notice I have my metal hoops more closely spaced at the bottom because yes, the depth, the pressure down here at this depth is greater than the pressure up here. Why is that? Well, simply because down here you're holding up more water. Up here, you're not holding up as much water. And here's that concept of the pressure at this house being greater than the pressure at this house. In fact, the pressure in this faucet being greater than the pressure in this faucet. And the pressure in this faucet being the greatest of all. Oh, and the pressure in this faucet being, not so great. These two look equal. Got to make that guy a little shorter. There. And if we had a faucet up here, the pressure there would be just piddly. The higher you are in this container, the less pressure there is. Number 10. A block of aluminum with a volume of 10 cubic centimeters. 10 cubic centimeters, that might be about 10 centimeters right there. So 10 cubic centimeter block of aluminum is placed in a beaker of water. And it was filled to the brim. Water overflows, dribble, dribble, dribble into my beaker here, splish, splash. Okay. All right, so we got this block, 10 cubic centimeters. The same is done with another beaker with a 10 cubic centimeter block of lead. Oh, what's the difference? Well, aluminum, Al, compared to doing the same thing with a block of lead of the same size. What's lead? PB, right? Lead, PB, not PD. Dyslexic here, for real. hey, there we go. Oh, start over. Same size block of PB, lead, and 10 cubic centimeters, 10 cubic centimeters, and water dribbles out into my little beaker, splish splash. There. Okay. The question is, what is the question? I don't know. Does the lead displace more, less, or the same amount of water? Well, the aluminum weighs a lot less than the lead. But because they are the same size, because they are the same volume, they are indeed going to displace the same amount of water. What's that tell you about the buoyant force then? Remember, the buoyant force has to be equal to the weight of the displaced water. So both the aluminum and the lead have the same upward buoyant force on them. Even though the aluminum weighs much less, lead weighs much more. But the buoyant forces are the same, because they are both 10 cubic centimeters. They are both 10 cubic centimeters. They are both displacing the same amount of water. Therefore, the buoyant force is the same, because buoyant force equals weight of displaced water. Related to that, number 11, a block of aluminum with a mass of 1 kilogram. Okay, we've got a 1 kilogram block of aluminum here. Is placed in a beaker of water to the brim. It overflows. Okay. The same is done with a beaker in another beaker with a 1 kilogram block of lead. Well, wait just a moment. This is 1 kilogram. The lead is also 1, but lead weighs more. How can that be? The lead block has to be a lot smaller in order to get PB, in order to get 1 kilogram, because lead weighs more. It takes more aluminum than lead to get 1 kilogram. So now, pretty clearly, which one is going to displace more water? The aluminum, being big, is going to displace more water than the lead, which is small. So, what are the questions exactly here? He says, does the lead displace more, less, or the same amount of water? The lead displaces less. It's not about weight, it's about volume. 1 kilogram of lead has less volume. 1 kilogram of aluminum has more volume. Number 12. A block of aluminum with a weight of 10 newtons is placed in a beaker of water filled to the brim. Okay, so this is 10 newtons. All right. Water overflows. The same is done in another beaker with a 1 kilogram block of lead. Wait a minute, am I in the wrong place here? Oh, I see what I'm doing. I was looking at number 12, which was not actually assigned. But let's look at number 12 anyway. So I got a 10 newton block of aluminum here. This is number 12. The same is done on a 10 newton block of lead. A 10 newton block of lead. Oh, this is like the same question. A 10 newton block of lead. Okay. Does the lead displace more, less, or the same amount of water? Why are your answers to this exercise and 11 different from your answers to number 10? Okay, yeah. Same story as number 11. I'm not going to take time to discuss it again because we just discussed it. It's really the same question. Number 14. There's a legend of the Dutch boy. I find out year after year how nowadays there are so few people who know the legend of the Dutch boy. It's kind of sad. When I was a kid growing up, everybody knew the legend of the Dutch boy. True story or not? I don't know. Exactly how does the story go? I don't know. But the idea is this. You've got the ocean. And then you got the Dutch town down here. All these houses. But it's below sea level. So you have to have this big old wall here to hold back the ocean. Well, actually this is kind of exaggeration. I'm sure houses were much larger than that. And you got this little kid one day, he's walking along, and he notices, oh no, there's a leak. And he sees water, yellow water I guess, he sees water that has found its way through a crack here, and the water is dribbling down out of this leak. Well, he knows how, he doesn't have a yellow head, don't be silly. He knows about leaks. He knows how these things work. This dike is just made of dirt, I guess. I don't know, dirt and rocks and things. And you notice that as water starts to come through here, it's going to erode it, and the water is going to dig a deeper and deeper and deeper hole, and before you know it, the whole dike is going to fall. So he very bravely sticks his finger in the hole and saves the town from destruction. Question is this: does that little kid and his little finger have enough strength to hold back the entire Atlantic Ocean? Well, yeah. Yeah, he's only like maybe 1 foot down from the surface. The pressure on this dike here at this elevation, the pressure does not depend on how wide the water is. Doesn't matter if this is a swimming pool or the Atlantic Ocean or the Pacific Ocean. Doesn't matter. What matters is how deep you are in the water. So sure, stick his finger in there, he can hold it back, no problem. There's not much pressure. Down here, say 1 foot from the top of the ocean, there's not much pressure there at all. It has nothing to do with the shape of the container. It has everything to do with the depth and the density of the liquid, of course. Number, that was 14. Number 17. Suppose you wish to lay a level foundation for a home on hilly and bushy terrain. How can you use a garden hose filled with water to determine the equal elevations for distant points? Well, I showed you that in the earlier demonstration. You take the hose. I'll grab a hose. One moment. I have my hose from the other day right here. It's not filled with any blue water, but we can pretend. And if I fill this hose with water, you know what happens. You saw it the other day. That the water levels on both sides are going to stay at the same elevation. No matter how I twist the tube back and forth, the water level in the two tubes will stay at the same elevation. So I can take one end of the hose and put it in the front of the house, the other end of the hose put it at the back of the house, and by watching where the water levels are, I can see where the same elevation from the front of the house to the back of the house is. After going through bushes and around trees and under the deck and all around everything else, I can still tell where the front porch is level with the back porch by looking at the water level in the hose. Pretty cool concept. Could be very useful. Number 19. Oh, this one's easy. We already alluded to it, sort of. If you cut your finger, why does holding it above your head reduce bleeding? Well, because you hold it above your head, now your finger is at the top of this container of blood, and therefore you have up there the lowest possible pressure. Yes, you do still have pressure because your heart is pushing the blood through the vessels, but up there you're going to have the least pressure. If somebody suggests to you, oh, your finger is bleeding, you better do something before you bleed out completely. Why don't you put your finger down near the floor? Well, that particular person is trying to get rid of you. That person wants you to bleed to death. No, down at the floor, you have the highest pressure, you're going to bleed the most. And perhaps more realistic, you simply are using a hammer and whack your thumb, and it really, really hurts and it's throbbing. You put it up high, it'll throb less. With each heartbeat, as the blood is pushed into that thumb, there'll be less pressure up here than if you put your thumb down low. Same thing with headaches. You put your head up high, reduce the pressure, it will feel a little bit better than if you put your head down low. Or if you're going to faint, just the opposite. You want to put your head down low to increase the pressure in your brain. If you feel, in fact, have you ever had the experience? Sure you have. Or maybe you're laying down on the couch watching TV and the fire alarm goes off and you jump off the couch and for just a moment you feel, whoa, a little bit faint. What's with that? Well, it takes a little bit of time for your heart to figure out that it's got to pump harder to get your blood flowing to the top of your head. When you're laying down, the heart is working less hard. It's working less hard. You jump up, now the heart is farther down, it takes more effort to pump the blood to your head, the heart falls behind a little bit, the blood leaves your head, and it's like, whoa, I think I feel kind of woozy. until your heart says, hey, we need to do something about this, and the heart starts beating harder and gets the blood pressure back in your head again. So very common. It doesn't mean you're dying or anything. That's normal. Number 21. Oh, last one of this particular part of the assignment. A can of diet drink floats in water, whereas a can of regular soda sinks. For real. Try it sometime. Diet drink, regular sugar-laden drink. You know, in one 12-ounce can of like Coke, there's something like, I forgot what the number is, it's something like 12, the equivalent of like 12 teaspoons of sugar. That's why I used to drink one Mountain Dew every day. I quit when I found out how much sugar is in those things. It's crazy. Anyway, sugar is more dense than sucralose or whatever they put in this stuff. The fake stuff, I call it, the diet stuff, is less dense than the real thing. And the real thing will sink in a bucket of water. The diet stuff will float. And since we're already done here and I've got some spare time, I'm going to tell you how you can make some money. Had this experience once, many years ago. A friend of mine had just gotten his doctorate in something or other, I don't know what, and he had a party at his house, and outside he had these big kegs that were full of ice water and bunches and bunches of sodas in there. And I looked in that thing, and I'm thinking, you know, I don't want that fake stuff. And all I'm seeing, floating in that ice water, all I'm seeing is the diet drinks. And then it occurred to me, of course, the real thing sinks to the bottom. Nobody knows that. Everyone thinks we're out of the good stuff. But no, all the diet stuff is floating. So you roll up your arms, your sleeve, and you reach down to the bottom of that bucket. Do you know how cold ice water is when you put your whole arm in? It's not pleasant. So it's quite a sacrifice. But you put your sleeve up, you reach in there, and you pull it out. Root beer, not what I wanted. No. Coke, no. Oh, my hand is freezing. Oh, man, that's cold. There it is, Mountain Dew. Got it, the real thing. Sugar laden, yeah, there it is. So here's what you do to make some money. You stand around near that keg of drinks there. Some other dude comes along, looks in there and says, oh, bummer, they're out of the good stuff, nothing but diet. And you say to him, tell you what, I can get you the real thing. $5 and I'll get you one. And he'll say, oh, yes, I'm desperate. I'll pay you $5. And so you tell him, yeah, just go around the back side of the house there and I'll bring it to you. Okay, thank you. Here's the $5. And after he's out of sight, it's worth $5, even as cold as it gets. And you take it to him and say, oh, thank you, where'd you find that? I don't reveal my sources. And you can make a bunch of money. Okay, we move on. No, we don't. We're done. Okay, so you already know what part 2 is. For the chieftain people, part 2 is due right now, same time as part 1. So we'll just load up the next video and keep on going. For the CLS people, your part 2 is due, if this is a Tuesday, it's due Thursday. If this is a Thursday, it's due next Tuesday. You know the story on that. And the test is coming soon for everybody. All right, so I sign off for now, and I will momentarily be diving into part 2, beginning at number 25. See you then.